So if you can, thank you again for a very nice talk. If you can unshare your screen. The next speaker is Debajyoti Sarkar from IIT Indore. Debajyoti, are you there and can you share your screen?
Yeah, hold on 1 second.
Very good.
Is it visible?
Yes,
yeah.
Please start.
I guess this is better.
Yes, fine. Please start.
Okay, yeah. So, yeah, thanks, Sunil, and thanks to the organizers for having me here and arranging this very nice conference. What I'm going to talk about is based on these two papers and some ongoing works with Kabat, Lifshitz, and Fuq. And in this paper, in this talk, what I'm going to mainly talk about is some ideas from quantum information theory and their applications in field theory in particular. And some of the quantities that I'll be dealing with is density matrices and the corresponding modular Hamiltonians. So I will have in mind the usual, you have some system in some pure state psi, and then you divide the system into two subsystems like A and A complement, A bar, and correspondingly you have the density matrices and the corresponding modular Hamiltonians. Now, actually, one of the important point of this talk will be the fact that these types of bipartitions of a system into some subregion and its complement is actually a bit imprecise in quantum field theory. And correspondingly, these operators like subregion modular Hamiltonians, HA or for HA bar, these are not very well defined in field theory due to UV divergences and so on. And in fact, a better defined quantity is the so-called extended modular Hamiltonians, which is defined like this. And in this talk, I will mostly compute these modular Hamiltonians and associated this extended modular Hamiltonian H for some excited state. And that excited state will be obtained by perturbing some modular Hamiltonian of a known state. So in particular, perturbing the vacuum state by some unitary operator G. So in terms of equations, we know some vacuum state we have in field theory. Suppose we know the corresponding vacuum state modular Hamiltonians. Let me call it H0. I will have some equations in a moment. And I go to some excited state by acting with some unitary operator. The operator looks like this. It has some Hermitian, local Hermitian operator smeared over some space-like or null hypersurface, this sigma, and with some support function f of x. And I will study what will happen to this corresponding modular Hamiltonian in this excited state. And then, we will also have some perturbative expansion parameter epsilon. And in some cases, we know the results exactly. And in some cases, we'll only know the results to the first order perturbation in epsilon. Because in general, finding out, excited state modular Hamiltonians, it's actually a very tough problem. So the framework in our case will be a field theory in arbitrary d dimensions, and we'll compute this modular Hamiltonian delta HA to first order in perturbations, as I said. And for most part, our subregion will be Rindler half space. And these are all these assumptions or these restrictions are put in place because otherwise it gets a bit difficult to compute it. I talked about this HA bar being a bit imprecise and having H being the better defined thing in quantum field theory, and it has to do with non-factorizability of Hilbert space. And it actually shows up in an interesting way in this excited state modular Hamiltonian. We'll provide a general form of this change in excited state modular Hamiltonian. So as you go from the vacuum state counterpart to the excited state counterpart for perturbations by some arbitrary modular weight n operator Jn. So this O is Jn. Whereby modular weight, I would mean that if you study the modular flow of these operators, of these Jn x's. So modular flow by vacuum state modular Hamiltonian H0, it's defined like this. And because, in our calculation, mostly this will be a Rindler half space, then these modular Hamiltonians are boost generators. And if the operator is modular weight n, then under this particular modular flow, it will transform like this. So in a sense, basically n will count the number of plus indices minus the number of minus indices for the J operator. And in fact, a good amount of work has been done on this problem. I mean, as you can see, there are papers starting from 2015, maybe even before. And in most of these in these papers, the expressions are quite abstract and formal. And in fact, I'll be using a result from Saras Yugajin, who has some formal expression given, you have some ground state to excited state transition, and there is a change in the corresponding density matrix. So there is a delta rho, and they gave an expression which connects the change in rho, this delta rho, with the change in the modular Hamiltonian's delta H. So we'll be using that, in fact. But what we have in addition to that is that we kind of distinguish between origins of various contributions to this delta H. And that's where we'll see that there are some surprising results. And also, most of these papers talked about stress tensor perturbations to the states, and the generalization to arbitrary n was mostly absent. And in fact, similar results also appear for stress tensor perturbations in these papers, where people studied modular Hamiltonians under shape deformation. So what they had in mind is that you have some subregion and you deform the subregion a little bit, and how does the modular Hamiltonian change, which you can think of in terms of the state being perturbed by the stress tensor. Now, before going to the meat of the calculations, let me say a few general things about what our expectations are or could be, and what the results that we find, and what are the kind of surprises and new things. So, if you have some perturbation over some spatial slice, and suppose you could factor out the spatial slice or partition this spatial slice in A union A bar, then that will imply that the perturbation that you are providing is also factored out in this form, like GA tensor, some identity plus identity acting on the A region tensor GA bar. And since GA and GA bar commute, this is some space-like slice, it would seem that the corresponding unitary transformations also factor, like U equals to UA tensor UA bar. And then it's like a one-line exercise to show that the corresponding reduced density matrices, modular operators, which are defined like this, which are in fact better defined quantity in field theory, they transform in this fashion. So, if you have U, some transformation unitary operator UA tensor UA bar, it factorizes between A and A bar, then rho A goes to this, rho A bar goes to this. And as a result, the modular operator delta goes to this, and the modular Hamiltonian also transforms in this fashion. So you just take the modular Hamiltonian of the, let's say, the two-sided modular Hamiltonian, this H double arrow here of the vacuum state, and you just do U H naught U dagger, and you get the excited state modular Hamiltonian. And this is, I mean, in all these lines, in all these steps, there are no assumptions except for the fact that the spatial slice has this bipartition A union A bar, and as a result G looks like this. But if this is true, then the first order change in the modular Hamiltonian would then be given by this commutator term. Now I'm particularly talking about the first order change because as I said, I will have some other methods to compute it, and there will only be considering the first order changes, because going to higher order sometimes are pretty difficult. So in any case, this is the exact result in that case, in this case. And in this case, the first order change will be like this commutator piece. And throughout this talk, whenever I say delta H commutator, I'll mean such a commutator piece at the first order. And then in the second order, it will be double commutator and so on and so forth. But it is actually only true, as we'll see, in the discrete systems, and it doesn't hold for QFTs. And in fact, there is an explicit, what I'll call an endpoint contribution, which arises from the surface separating the two subregions A and A bar. Okay, so in fact, we will find that delta H is not just delta H commutator, but an extra piece. To first order, I'll call it delta H endpoint. And in fact, you can call delta H endpoint anything which is not a commutator piece. And these are our results. We'll see that this endpoint contribution vanishes for certain perturbations, especially for perturbations with modular weights -1, 0, and 1. And if you have perturbations by stress tensor, which is modular weight 2, n equals to 2 or 3, 4, etc., you have only studied integer modular weights, then the corresponding endpoint perturbation exists. It's a non-zero quantity, and it goes like this. So the total delta H is delta H commutator, which we'll expect, plus this quantity. And this quantity is interesting for several reasons. But first of all, I should mention that these quantities have been studied in literature. These are known as light ray operators. And in particular, here we also have moments of light ray operators. So basically, you see that as the endpoint piece, we have these perturbing operator Jn and their descendants. And they are integrated over x plus horizon for positive modular weight, and there is a similar result for negative modular weight, where the endpoint contribution will be a light ray operator over the x minus horizon. And then there are also quantities which appear here, which is fk0. So remember that in G, if you remember from few slides ago, there were the support function f of x. And if the support function is non-zero and the derivatives are non-zero, they will actually appear and make this delta H endpoint non-zero. And then I also have this theta parameter here, which basically tells me the location of this space-like slice sigma, how much it is tilted from the x plus horizon, because it's a space-like slice for now what I'm considering. I'll have some picture in a few slides. Okay. So this is the main result that I want to convey, that you get light ray operators and their moments, these various moments with k and l exponents going, taking these types of values. The simplest example is a stress tensor perturbation in CFT2, in which case, if you evaluate this quantity, it will be the so-called NX operator, which is basically the stress tensor integrated over the x plus horizon. Okay, so this is the result. By the way, feel free to ask me questions at any point of time, or we can just defer to the end of the talk. But having said all this, the results, let me now go back to a very simple case, especially for the case of stress tensor perturbation, where we can compute these quantities in a very simple and alternative way. And then I will talk about a more general way of computing this. So just to, make sure that I'm not being crazy, and you can see these calculations, these quantities arising very easily, or in a very well-defined setting, rather. So I'll have in mind some CFT2 vacuum perturbed by stress tensor. There, for any even finite region, you don't even have to go to Rindler subregions. For any region U2V, the vacuum state modular Hamiltonian the expression is well known. And you can go to this excited state that I was considering by doing a conformal transformation Z to G of Z, some local conformal transformation to change the state. And you can, in fact, compute then what is the corresponding excited state modular Hamiltonians by just implementing this resulting conformal transformation in this equation. And the result turns out to be this. And to kind of touch base with the results I showed, we can take G of Z, this transformation, this conformal transformation, to first order epsilon as this. Sorry?
Shouldn't there be a Jacobian factor in the HUV compared to, because the measure should have a Jacobian factor, right?
Yeah, so you have some G prime of Z arising from there.
Okay.
Yeah. So we'll be interested in this linearized perturbation to kind of match with the results I showed you before, the general result. And that will actually correspond to perturbation by stress tensor with this generator. The G, capital G, is the capital G I showed you before for stress tensor perturbation. And then so you can readily compute it. You just plug in this value of G of Z in here in this equation, and then you just expand to first order in epsilon. And the result is this. So the first order in epsilon is, of course, the leading order, the epsilon to the 0 order result is, of course, H naught UV. So the change in H, the H UV minus H naught UV, is given to first order in epsilon by this quantity, what I have on the second line. Now, this is interesting because the first line only is the commutator contribution, which you can explicitly check because you can use TT commutator relations and you can compute minus epsilon G comma H0, and that will give you this first line. But this second line, you see, it vanishes if the support function were 0 at the endpoint. But in general, in QFT, it is not 0, right? Because the perturbation is all over the place from some, from across the endpoint. Some, if it is from U to V, so somewhere from less than U to greater than U, and if to V, then somewhere from less than V to greater than V. So this second line is the endpoint contribution, and it will vanish if it were so that FU and FV are 0. Okay, so in that case, of course, I can also actually bipartite the two systems as A union A bar, for the Rindler cases, for example. And you can also make contact with the Rindler results. So we have done it here. So you can zoom in on the endpoints by choosing some f of x, which looks like this. So we have assumed that, so this is one of the endpoints, this crosshair here. And we have assumed that this support function is constant across this endpoint. Doesn't matter if it's not constant, but here for simplicity, I've considered it to be constant. So f of x is of this form. And then if you go to the Rindler Hamiltonian case, which corresponds to some 0 to infinity subregion, so you put u equals to 0 and v to infinity, then you get this result. And then if you take a to b 0, a and b to 0, so a and b was some two very small separated regions across the endpoint. So the perturbation were straddling the endpoint. So only after computing this, I want to take that, the support of f to 0. And then you see that some non-zero piece is remaining. And this non-zero piece is precisely this NX operator that I was talking about before. Okay, so to begin with, if you naively thought that, okay, if a and b is 0, then it's, there is no perturbation there, and then everything vanishes. So there is no contribution of delta H coming from there, but that's actually not true if you do it properly. So this is, this is a very straightforward calculation, and it already shows you that indeed, if you just considered sigma as a union A bar, then you would be missing something in field theories.
Debajyoti, you have 5 minutes. Is that okay?
Yeah, I'll try my best. Okay, so I'll now try to derive this delta H in a general operator method. So, not for all operator perturbations, you will have this conformal transformation techniques. So I'll start with this vacuum state. I'll write it in this Smith decomposition form. From there, you can calculate rho A naught and rho A bar naught. And then we go to some excited state excited by these types of operators. So G is GA tensor GA bar, where GA tensor GA bar form is a more general case of what I was considering before, which was GA plus times identity plus identity times GA bar. And then you can get some expression of delta rho A, not important. Let's move on. Then you can actually simplify this result quite a bit by using something known as modular conjugated operator. So for Rindler subregion, this J becomes CPT. So in general, this J appears in Tomita Takesaki modular theory, where if you know about this Tomita operator S, you can decompose as J delta to the half, where delta is the modular operator and J is the modular conjugation operator. But for Rindler, it's a CPT conjugate. So in terms of this GA bar tilde, which is the modular conjugate operator of this perturbation, which working on GA bar, you can write down delta rho A in this form. And as you can see, this delta rho A is already not in the form of a commutator like G8, rho A naught because of this GA bar piece. And then we use the Sarkar formula. This is the formula which relates delta rho A with delta HA. So the delta HA is given by, almost a modular flow of delta rho A, the change in the density matrix as you went from one state to another. And basically what we will do, we'll substitute this expression in here. So that's what we did here. And basically, it can be written in this simple form by, realizing that the modular float operator, any operator at some modular parameter value S is defined by this quantity. So we'll be coming back to this expression for what we are doing next. So we'll have to identify what is G and what is GA bar, and then implement it here. So now, so this is the most general case. We have some space-like perturbation over this blue slice here. And here, naively, what we'll do is that acts from 0 to A, and by GA bar, we'll define the perturbation which acts from 0 to minus B by some operator Jn with some support function f of x, as we discussed before. And the point is that we'll have to then be very careful about what goes on at the endpoint to actually extract the result. And then if you plug this G and GA bar back into this Sarkar formula, what you will get is this. So there are many things that are important. For example, there are in the Sarkar formula, you will have a situation where the modular flow is by some imaginary modular parameter. And you also have this GA bar tilde pieces, which you have to take care of. So for example, to take care of this imaginary modular flow, we have defined it to some imaginary value S minus IR, and then have taken from R equal to 0 to pi. So that helps us keep track of things. And for concreteness, we'll study this delta HA inside a correlation function of J and Y. And only in conjugation of that, in fact, we'll see that as you go to large modular parameter values, S going to plus minus infinity, or if you define W as e to the minus S for W equal to 0 and infinity, they have well-defined correlators. So basically, our goal will be to study the correlators of this type. So for concreteness, we will consider some CFT primaries as Jn, and so that we can write down these correlators. And we'll have various branch cuts in these correlators. And these branch cuts will look like this in this W plane. So now we are going from S to this W plane by e to the minus S is W. And in this W plane, the branch cuts will look like this. And all you have to do is to do this W equal to 0 to infinity integral here, this W equal to 0 to infinity integral here, keeping track of all those branch cuts and the rotation of the branch cuts as you take the modular flow in this S minus IRR from 0 to pi. Okay, so once you do that, the contour prescription will look like this. And basically, this will be your expression. And then you can hope to strip off this J and Y and to obtain the expression of delta H. And then I will just simply tell you the results because I'm out of time. So if the perturbations were acting on the A region alone, so that the A bar there were no perturbation in A bar at all, then the contour prescription will look like this. And there is also a pole at -1. So if you can do these integrals. In fact, what happens is that in these correlators, you can actually, due to this property, which I very briefly mentioned, you can actually close the contour at 0 and infinity. So because these are closed contours with a minus sign, you can actually enclose this -1 pole, and that gives you the commutator contribution here. On the other hand, if the perturbation was only acting on A bar, then all the branch cuts will be in this direction and the contours will not include anything, and it will give you 0. And this is exactly what you would expect, because if the perturbation is in A alone, there is no endpoint contribution and it will be the commutator piece. And if it is on the A bar alone, then the change in delta HA will just be 0, because you are not perturbing in the A region. And then if the perturbation straddles the endpoint, the calculation gets a bit trickier. I'll not bore you with the details, most importantly because I don't have time, but let me just show you the final results. Basically, the final result will look like what I showed you in the beginning. That in the discussion sections, if I am given the chance, or if you ask, I can go back and show you the calculations. But basically, the quantity that we are looking for here, sorry, 1 second. So in this case, delta HA, if I write it as fx plus ix plus, then after some careful calculations, you can calculate this ix plus as this quantity. So the ix plus gives you some commutator piece for the far away from the endpoint case, and some piece which is precisely what I advertised before, which are the moments of light ray operators. So the takeaways is basically, I have only 2-3 slides left, so I'll be very quick. The takeaways are that for a generic perturbations like this, the endpoint contributions are given by these light ray moments. And in fact, these light ray moments satisfy precisely the some of the properties that we wanted to satisfy. For example, if you just look at the generic properties of modular Hamiltonians, you can show that the modular Hamiltonian of any state actually annihilate the states. So if you apply H acting on psi equals to 0 and expand it to first order in epsilon, you can show that you get the delta H endpoint. If you define delta H as commutator plus the endpoint piece, then you can show that the delta H endpoint should annihilate the vacuum state. And precisely these these light ray moments are such that we are getting light ray moments of that many order that actually has the property that it annihilates the vacuum state. So everything seems to work out properly. So yeah, I think I'm over time, or maybe done with the time. So I'll just flash the future directions, that there are many things. We have actually more questions than we have answers. For example, for most cases, I consider Lindler's, but what happens for finite subregions, something that can be done for time-like perturbations or higher order contributions. One can ask that, okay, for these NX operators, you have a statement of positivity, whether that also goes through for these light ray moments. We were interested in this from bulk reconstruction perspective, because there is a modular Hamiltonian way of doing bulk reconstruction. So we wanted to do it for excited state. So these are all some future questions. And with that, I thank you.
Thank you very much, Debajyoti. So we have time for 1 or 2 questions.
Yes.
Somdat has his hand up. Somdat, you can go ahead.
So when you are talking about zero state Hamiltonian and excited state Hamiltonian, what do you exactly mean? Because
I had in mind only vacuum state as the zero state, and the excited states are perturbatively close to the vacuum state. So if I can go back to very briefly to my this initial slides. So this is what I had in mind. So for vacuum state, I know what my modular Hamiltonians are for Lindler subregions, and I used that and this ideas of modular flows to find out some modular Hamiltonians to this excited state.
Okay.
No,
are there any more questions? Okay, if not, then let's thank Debajyoti. So you can